In the silent, vast theater of the cosmos, countless stars burn like celestial campfires, each one a colossal nuclear furnace pouring unimaginable energy out into the empty dark. Our own sun, a modest and gentle star, unleashes more power in a single second than humanity has produced in its entire history. Yet we, on our tiny distant world, catch only the barest whisper of this energy, less than 1/2 billionth of its total output. The rest radiates away, a cosmic fortune lost to the void. But what if a civilization grew beyond the needs of a single planet? What if their thirst for energy became so great they sought to capture not a fraction of their star's power, but all of it? Tonight, we journey into the realm of cosmic megastructures, to the ultimate expression of technological ambition. We will explore the science, the scale, and the staggering implications of building a cage for a star. This is the story of the Dyson Sphere. Prepare yourselves for a voyage into engineering beyond imagination. We begin. Every action you take, every thought you have, every beat of your heart is a transaction of energy. From the smallest microbe to the largest galaxy, all of existence is governed by a constant, unending flow of power. For life and for civilization, energy is everything. It is the currency of progress, the fuel of creation, and the ultimate measure of a society's reach and capability. Throughout our history, every great leap forward, from the mastery of fire to the harnessing of steam to the splitting of the atom, has been a story of unlocking a new and more potent source of energy. We have built a global civilization by drinking from the shallow pools of power available on our planet's surface, the stored sunlight and fossil fuels, the kinetic force of wind and water, the heat from our planet's core. But these are just puddles, temporary reservoirs on a world that is itself a cosmic island, and our thirst is growing. In 1964, the brilliant Soviet astronomer Nikolai Kardashev was contemplating a question of profound significance. How might we detect other intelligent civilizations in the galaxy? He reasoned that while their biology, their culture, and their language might be incomprehensibly alien, one thing would be universal: their need for energy. A truly advanced civilization, he proposed, would eventually outgrow the limited resources of its home planet and begin to harness energy on an astronomical scale. To classify these hypothetical civilizations, he created a simple, elegant, and terrifyingly ambitious framework that would become known as the Kardashev scale. It is a ladder of cosmic power, a way to rank civilizations not by their philosophy or their art, but by the sheer raw wattage they command. A Type 1 civilization, on the Kardashev scale, is a planetary civilization. It has achieved mastery over its home world, capable of harnessing the total amount of energy that falls upon it from its parent star. This includes all forms of terrestrial power: solar, wind, geothermal, and nuclear. A Type 1 civilization can control the weather, prevent earthquakes, and manage the resources of their entire planet with perfect efficiency. The total power they would command is roughly 10 to the power of 16 watts. As of today, humanity is not yet on this scale. We are a Type 0 civilization, still drawing our power primarily from the dead plants and animals of our planet's past. Physicist Carl Sagan estimated that we currently reside at about a Type 0.73 on the scale. We have a long way to go before we can even be considered true masters of our own small house. A Type 2 civilization is a stellar civilization. It has graduated from the limited energy budget of a single planet and has begun to harness the full, undiluted power of its home star. A Type 2 civilization would not just be catching the sunlight that happens to fall on their world, they would be capturing the entire energy output of their star in all directions. The power they would command is a staggering 10 to the power of 26 watts, 10 billion times greater than a Type 1 civilization. This is the level of power that could sustain a population of trillions, fuel interstellar travel with ease, and power computers the size of planets. A Type 2 civilization would be, for all intents and purposes, immortal, their survival no longer tied to the fragile fate of a single world. And then, there is the final step on the original scale, a Type 3 civilization. This is a galactic civilization. It has transcended the power of a single star and has learned to harness the energy output of its entire home galaxy. They would command the power of 100 billion to 400 billion stars simultaneously. The energy at their disposal would be 10 to the power of 36 watts. They could manipulate space-time, move entire star systems, and power computations on a scale that borders on the divine. A Type 3 civilization would be a true galactic empire. their influence spreading across 100,000 light-years. To put this into perspective, let us use an analogy. Imagine your energy source is a single, small campfire. This is the energy available to a pre-industrial society, a Type 0 civilization. Now imagine you learn to harness the power of every single lightning strike that hits the entire planet simultaneously, every second of every day. That is a Type 1 civilization. It is a level of power that makes the campfire seem insignificant. Now imagine you are no longer content with the lightning. You decide to build a shell around the entire sun itself to capture its full, unblinking thermonuclear fury. That is a Type 2 civilization. It makes the power of the planet's lightning seem like a single, flickering candle, and a Type 3 civilization. That would be like capturing the combined light of every campfire, every lightning bolt, and every star in the entire Milky Way galaxy. It is a level of power so far beyond our current comprehension that it enters the realm of mythology. The Kardashev scale is more than just a science fiction trope. It is a profound guide for our search for extraterrestrial intelligence, or SETI. If we are looking for radio signals from another Type 0.7 civilization like ourselves, we are looking for a needle in a cosmic haystack. But a Type 2 civilization would be impossible to miss. They would be a beacon in the dark. A civilization consuming the entire energy of its star would by necessity fundamentally alter the appearance of that star. They would be broadcasting their existence to the cosmos, not with language, but with the brute force announcement of stellar scale engineering. And this brings us to the central question. How? How could any civilization, no matter how advanced, possibly hope to capture the entire output of a star? You cannot simply build a giant solar panel the size of a planet's orbit. The engineering challenges are monumental, the materials required are astronomical, and the sheer scale of the project is enough to shatter the human imagination. Yet, a physicist and astronomer named Freeman Dyson, contemplating this very problem, came up with an idea so audacious, so elegant, and so terrifying in its implications that it has captured the imagination of scientists and dreamers for over half a century. He envisioned a way to build a cage for a star. He envisioned the first and most iconic of all cosmic megastructures, and in doing so, he gave us a tantalizing and perhaps achievable blueprint for the birth of a Type 2 civilization. In the year 1960, a brilliant physicist and mathematician named Freeman Dyson, working at the Institute for Advanced Study in Princeton, New Jersey, published a short, two-page paper in the journal Science. The paper was titled, "Search for Artificial Stellar Sources of Infrared Radiation." In it, Dyson was not proposing a feat of engineering. He was proposing a strategy for discovery. He was thinking like a cosmic detective, asking himself what kind of evidence a truly advanced, energy-hungry civilization would leave behind. He was looking for a celestial fingerprint, a clue that would betray the presence of intelligence on an astronomical scale. Dyson started with the same premise as Kardashev, that a mature civilization's energy needs would eventually grow so vast, they would be compelled to utilize the full power of their star. He imagined them breaking down their home planet, and perhaps the other planets in their solar system, to use as raw materials for a monumental construction project. He envisioned them building a vast complex of orbiting structures, a cloud of habitats and solar collectors, that would eventually grow so thick and dense that it would completely surround their parent star, forming a shell. This hypothetical megastructure, which would later be named the Dyson Sphere in his honor, would be the ultimate power plant. It would intercept every single photon, every particle of solar wind, every iota of energy leaving the star in all directions. It would be the mark of a true Type 2 civilization. But Dyson's genius was in realizing what this would look like to an outside observer. An alien astronomer, like us, looking at a star that has been enclosed in a Dyson sphere, would not see a star. The sphere would block all of the star's visible light. The star would, in effect, vanish from the sky. But the laws of thermodynamics are absolute. Energy cannot be created or destroyed. It can only be converted from one form to another. The civilization inside the sphere would be capturing all of the star's high-energy visible and ultraviolet light. They would use this energy to power their society, their computers, their industries. But any process, no matter how efficient, generates waste heat. All of that captured stellar energy would eventually be degraded and re-radiated back out into space. But not as visible light. It would be radiated away as low-energy, long-wavelength infrared radiation, the signature of waste heat. Therefore, Dyson argued, If we are searching for these advanced civilizations, we should not be looking for radio signals or visible clues. We should be looking for ghosts in the star field. We should be searching for large, warm, dark objects that are pouring out colossal amounts of infrared radiation. We should be looking for the heat signature of a star-sized radiator, an object that is as luminous as a star, but which is shining at a temperature of only a few hundred degrees, the comfortable room temperature of the civilization living inside. It would be an artificial nebula, a star that has been cloaked from sight, its presence betrayed only by its own colossal technological fever. Now, it is crucial to understand what Dyson was and was not. Proposing, the popular image of a Dyson sphere is that of a single, solid, rigid shell completely encasing a star, a giant metallic sphere with a star at its center and a civilization living on its inner surface. While visually stunning, this concept is a physical impossibility. A solid shell of this size would be gravitationally unstable. The slightest nudge from a passing comet or a gravitational tug from a distant planet would cause the sphere to drift. Eventually, it would collide with its own star, resulting in a cataclysm of unimaginable proportions. Furthermore, no known material could possibly withstand the immense tensile and compressive forces required to build a solid spinning sphere 93 million miles in radius. The structure would tear itself apart under its own weight. Dyson himself was well aware of this. His original concept was far more elegant and far more plausible. He did not envision a solid shell, but rather what we now call a Dyson swarm. To understand the difference, let us use an analogy. The impossible, solid-shell Dyson sphere is like trying to build a single, solid, seamless dome over an entire city. The engineering is a nightmare. The dome would collapse under its own weight, and a single crack could compromise the entire structure. A Dyson swarm, on the other hand, is like demolishing every building in that city and replacing each one with a skyscraper that has its entire roof covered in solar panels. Then you continue building more and more of these solar panel-topped skyscrapers, filling in every park, every street, every square inch of the city, until the entire urban area, when viewed from above, is a continuous, unbroken blanket of solar collectors. There is no single dome. Instead, there is a vast, independent, yet coordinated, collection of millions or even billions of individual structures, all working together to achieve the same goal: to block out the sun. This is the Dyson swarm. It would be a cloud of countless independent solar collectors, power stations, and habitats, all on their own unique, intersecting orbits around the central star. Each collector would be like a giant robotic dragonfly, its wings made of vast solar panels, drinking in the starlight and beaming that energy, perhaps via microwave or laser, to habitats within the swarm. The swarm could be built gradually. A civilization could start with a few collectors, then a few thousand, then millions, adding to the swarm over centuries or millennia as their energy needs and their industrial capacity grew. There would be no single point of failure. The destruction of one collector would be insignificant. The orbits would be carefully managed by advanced artificial intelligence to prevent collisions, creating a flowing, dynamic, and ever-changing celestial beehive around the central stellar fire. The sheer scale of such a project is difficult to articulate. To build a Dyson swarm around a star like our Sun, at a distance similar to the Earth's orbit, would require a staggering amount of material. If each collector had a thickness of just 1 meter, the total mass of the swarm would be equivalent to the entire mass of the planet Jupiter, the largest planet in our solar system. A civilization undertaking this project would almost certainly have to completely dismantle all of the terrestrial planets, all of the asteroids, and all of the gas giants in their home system to gather enough raw material. It is a project that would require the industrial output of an entire solar system for thousands of years. It is the ultimate act of planetary demolition and celestial reconstruction. The completion of a Dyson swarm would be the moment a civilization graduates to a Type 2 status. They would be the undisputed masters of their stellar domain, their existence powered by a machine the size of a solar system. But Dyson's idea was not just a blueprint for future engineering. It was a call to action for the astronomers of today. It gave us a specific, testable hypothesis. It told us that if these civilizations are out there, they will be shining with a light that is invisible to our eyes, but brilliant to our infrared telescopes. The ghost in the star field might not be a ghost at all. It might be the warm, breathing, and very much alive signature of the most powerful beings in our galactic neighborhood. The hunt was on. Before a civilization can dream of caging a star, before the first orbital habitat is launched, or the first solar collector is forged, they must confront a terrible and unavoidable truth. The price of a Dyson swarm is worlds. The construction of a machine the size of a solar system requires a quantity of raw material so immense that it cannot be found in the lonely asteroids or the distant comets. The only sufficient source of matter is the planets themselves. The great project begins not with a blueprint and a rivet gun, but with a demolition order for an entire solar system. The builders of a Dyson swarm must first become the eaters of planets. The sheer mass required is the first great filter, the first barrier that separates a planetary civilization from a stellar one. As we've discussed, a Dyson swarm around a sun-like star would require the equivalent mass of the planet Jupiter. Jupiter is a gas giant, but its core is thought to contain a vast quantity of rock and metal, perhaps 10 to 15 times the entire mass of the Earth. But even this would not be enough. The swarm would require colossal amounts of structural materials like iron, nickel, and carbon, and semiconductor materials like silicon. The most efficient and logical place to find these heavy elements is in the terrestrial rocky planets that orbit close to the star. Mercury, with its massive iron core, Venus, with its dense silicate mantle. Even the civilization's own home world, their cradle of life, might not be spared. In the grand calculus of a Type 2 civilization, a single planet is but a temporary convenience, a stepping stone. A star's full power is the eternal prize. To achieve this, the civilization would have to embark on a project of planetary deconstruction. This would not be a fast or explosive process, like a science fiction Death Star blasting a planet to rubble. That would be messy, inefficient, and would scatter precious material across the solar system. The disassembly of a planet would be a slow, methodical, and industrial process, likely taking thousands of years for each world. It would be the ultimate act of mining, a strip mine operation on the scale of a celestial body. Imagine you decide to build a single solid brick wall that completely surrounds your home city, a wall that is a mile high and 100 feet thick. You quickly realize that importing the quadrillions of bricks you would need is a logistical nightmare. The only truly efficient solution is a terrifying one. You must start demolishing the city to build the wall. You would systematically tear down every skyscraper, every bridge, every stadium, and every house. You would grind the concrete and steel down into aggregate and feed it into automated brick-making factories. You would consume the city to enclose the city. This is the brutal logic that a Dyson-building civilization must embrace. They must consume their own solar system to build their new home. The planets, once seen as worlds, as destinations, become nothing more than quarries. They are transformed from places into piles of raw material. The technology required for such a task is, from our perspective, indistinguishable from magic, but the likely workhorse of this demolition would be a fleet of self-replicating robotic probes. These are often called von Neumann probes, named after the brilliant mathematician John von Neumann, who first conceived of them. A von Neumann probe is a robot that contains the instructions and machinery to build a perfect copy of itself using raw materials from its environment. You would send a single master probe to a planet like Mercury. It would land, begin mining iron and silicon, and use those materials to build 2 new probes. Those 2 probes would then build 4. The 4 would build 8. In a shockingly short amount of time, an exponential cascade of replication would create a swarm of billions or even trillions of mining robots that would systematically dismantle the entire planet, molecule by molecule. This army of machines would operate with inhuman patience and precision. They might strip mine the surface, digging continent-sized pits miles deep. They could deploy vast fields of solar-powered mass drivers, electromagnetic catapults, that would launch refined materials into precise orbits where they could be collected by larger factory ships. They might even resort to brute force methods, redirecting large asteroids to impact the planet, blasting billions of tons of crust and mantle into space, a controlled and sustained act of celestial bombardment. For the gas giants like Jupiter and Saturn, they might deploy vast automated atmospheric scoops, giant refineries that would dive into the thick clouds to filter out the trace amounts of heavier elements. Or they might engage in a process known as starlifting, using immense magnetic fields to pull hydrogen and helium directly from the star itself to use as fusion fuel for the entire operation. The numbers associated with this planetary feast are humbling. The mass of Jupiter is approximately 1.9 times 10 to the power of 27 kilograms. This is more than 318 times the mass of the Earth. To unbind the gravity of a planet like Earth, to take it apart piece by piece and lift it into orbit, would require an amount of energy equivalent to the Sun's entire output for several weeks. The civilization would need to be well on its way to becoming a Type 2 society just to have enough power to start the demolition phase. The timescale for this process would not be measured in years, but in millennia. It would be a slow, patient, and relentless consumption of their own birthplace. This phase of development raises profound philosophical questions. What happens to a planet's biosphere if one exists? A civilization capable of dismantling planets has surely moved beyond the need for a single biological cradle. It is likely they would have already transitioned to a post-biological existence, their consciousnesses uploaded into vast computational networks. Or perhaps they would see it as their duty to preserve the life of their home world, building colossal self-contained habitats, cosmic arcs, to house their planet's ecosystem while its physical body is consumed. We can only speculate, but one thing is certain. A civilization that commits to building a Dyson swarm is a civilization that has consciously decided to sever its relationship with the past. It is an act of ultimate commitment to a technological future, a future where the concept of a home planet has become obsolete. They are not just building a power station, they are building their own custom-made universe. And the price of entry is everything they have ever known. But once the price is paid, once a Jupiter mass of carefully refined elements is waiting in a vast, dusty ring around the star, the second and even more complex phase of the project begins. The demolition is over. The solar system is a ghost of its former self. Now the challenge shifts from destruction to creation. The civilization must ignite the celestial forge. The old solar system is gone. The planets, once vibrant worlds of rock and gas, have been ground down into a diffuse, orbiting cloud of raw elements. A ghostly ring of iron, silicon, carbon, and nickel now encircles the central star, a primordial soup waiting for a cosmic chef. The era of demolition has ended. The era of creation is about to begin. The civilization must now construct the celestial forge, a factory the size of a planetary orbit, a manufacturing system of such breathtaking scale and complexity that it will transform this dust into the greatest engineering project in galactic history. The construction of the Dyson swarm would not happen on a planet. Building billions of continent-sized structures in a gravity well and then launching them into space is a fool's errand, a colossal waste of energy. The entire manufacturing process would take place in zero gravity, in a series of vast automated orbital factories. These factories themselves would be the first things built from the processed planetary matter. They would be the heart of the celestial forge, the great robotic motherships that would give birth to the swarm. To understand the logic of this construction, we must think of it not as a linear process, but as an exponential one. It is a project that powers its own growth. Imagine the process as a kind of cosmic 3D printer. The ring of raw material around the star is the printer's filament. The automated factories are the printer heads, and the grand complex design of the swarm's orbital mechanics is the blueprint loaded into the printer's memory. The process would begin by printing a single master satellite. This first collector would be a marvel of engineering, but its most important purpose is to provide the energy to accelerate the process. Once it is operational, its captured solar power would be beamed to the factories, allowing them to build 2 new satellites in the time it took to build the first one. Those 2 new satellites would then add their power to the grid, allowing the factories to build 4 more, then 8, then 16, then 32. The construction would bootstrap itself, a chain reaction of manufacturing. The project would start agonizingly slowly, but in its final stages, it would become a blindingly fast explosion of creation, with millions of new collectors being added to the swarm every single day. The basic building block of the swarm, the individual Dyson collector, would be a masterpiece of efficiency. It would not be a heavy, armored battle station. It would be a creature of pure function, designed to be as large and as lightweight as possible. The most likely design would be a vast gossamer thin sail, a STITE short for static satellite. A STITE would be a huge solar sail, a mirror-like surface perhaps hundreds of miles across, but only a few molecules thick. It wouldn't technically be in orbit. Instead, it would use the gentle, continuous pressure of sunlight itself to perfectly balance the star's gravitational pull, allowing it to hover in a fixed position in space. This design would minimize the need for propellant and complex station keeping, making the swarm far more stable and long-lasting. Each of these statites would be a fully autonomous robot. It would have a brain, a sophisticated artificial intelligence responsible for maintaining its position, managing its power systems, and communicating with the rest of the swarm. It would have its own navigation system, perhaps using tiny ion thrusters to make fine adjustments to its orientation. And it would have a transmitter, a powerful laser or microwave emitter that would form a tiny part of a vast star-sized phased array, beaming the collected energy to a central storage system or directly to the civilization's habitats. These habitats themselves would be part of the swarm colossal O'Neill cylinders or Bernal spheres, artificial worlds providing trillions of beings with a comfortable, controlled environment. The sheer scale of the completed swarm is a number that breaks the mind. In the surface area of a Dyson swarm built at the Earth's orbital distance from the Sun is approximately 280 quadrillion square miles. That is 600 trillion times the surface area of the planet Earth. Let that number sink in. You would have a living and working area 600 trillion times greater than all the continents and oceans of our world combined. Even if each individual collector was the size of the state of Texas, you would still need more than 1 billion of them to complete the swarm. Managing this celestial beehive would be the single greatest logistical and computational challenge imaginable. Billions of independent continent-sized platforms, all hovering in a dense shell around a star, must be perfectly coordinated. The AI network governing the swarm would have to track the position and status of every collector in real time, constantly making minute adjustments to prevent collisions and to optimize power collection. It would need to manage traffic control for ships moving within the swarm. It would have to be a self-healing system, automatically dispatching repair drones to fix collectors damaged by micrometeoroids or deorbiting and recycling collectors that have reached the end of their operational lives. A Dyson swarm would not be a static, dead machine. It would be a living, evolving, thinking ecosystem of robots and artificial intelligences, a single, integrated machine the size of a solar system. We have now gathered the materials. We have established the celestial forge. We have populated the space around a star with a thinking, self-assembling cloud of technology. The civilization has achieved its goal. They are now capturing 100% of their star's energy output, a colossal 400 septillion watts of power every single second. But for what? Why go to all this trouble? Simply keeping the lights on for a population of trillions, while impressive, does not seem to justify the deconstruction of an entire solar system. The true purpose of a Dyson swarm, the ultimate application of a Type 2 civilization's power, is not just to sustain life. It is to create a new form of life. It is to build a computer and a mind the size of a star. The star is caged. The swarm is complete. A civilization has achieved total mastery over its solar system, commanding a continuous flow of energy so vast it is nearly impossible for a planetary mind to hold. 400 septillion watts of power. The full thermonuclear fury of a star is now on tap. But for what grand purpose? Simply powering the cities and transportation for a civilization of trillions. While a monumental task, seems an almost trivial application for a machine that required the sacrifice of entire worlds. Type 2 civilization would not look at their star and see a mere power plant. They would see the ultimate component of an even grander machine. They would see a central processing unit. The ultimate goal of a Dyson Sphere is not just to power a civilization. It is to power a single unified computational consciousness. The goal is to build a brain the size of a solar system. This is the concept of the Matryoshka brain, an idea even more ambitious than the Dyson swarm itself. Proposed by the futurist Robert Bradbury, it is a design for a computational device of literally astronomical proportions, and it is the most thermodynamically efficient way to use a star's energy to think. The name comes from the famous Russian Matryoshka nesting dolls, where a series of smaller dolls are packed one inside the other. A Matryoshka brain is a set of nested concentric Dyson spheres, each one using the waste heat from the sphere inside it to power its own computations. Imagine the structure. At the very center is the star, the ultimate power source, burning at millions of degrees. Surrounding it is the first and hottest Dyson sphere. This innermost layer would be a computer operating at a temperature of thousands of degrees, as close to the star as material science allows. It would be made of exotic materials capable of withstanding this inferno. This sphere would perform colossal computations, and in the process, it would generate an enormous amount of waste heat, just as your laptop gets warm when it is working hard. But this heat is not lost. It radiates outward and is captured by a second, much larger Dyson sphere that completely encloses the first. This second layer would be a computer designed to operate at a lower temperature, perhaps a few hundred degrees. It would perform its own vast computations, and its waste heat would in turn be captured by a third, even larger sphere. This process could continue, with 4, 5, or even dozens of nested layers, each one larger and cooler than the last, until the final outermost sphere radiates its waste heat into the cold of space at a temperature just a few degrees above absolute zero. Let us return to our analogy of the Russian nesting dolls. The star is the tiny, solid, innermost doll, the source of all the potential. The first Dyson sphere is the next doll that fits snugly over it. Its body is a massive computer, and the heat from the inner doll is what brings it to life. But as it thinks, its own body gets warm. This warmth is then used to power the next slightly larger doll that fits over it. That doll thinks, gets warm, and powers the next one. The entire nested set, from the blazing hot inner layers to the freezing cold outer layers, forms a single colossal thinking machine. Every joule of energy from the star, from the highest energy gamma rays to the lowest energy infrared photons, is captured and used for a productive computational purpose before it is allowed to escape. It is the perfect engine of thought. But what would such a machine be thinking about? The computational capacity of a Matryoshka brain would be so far beyond our own experience that we can only speculate. It would not be balancing spreadsheets or rendering videos. It would be engaged in what we might call metaphysical engineering. One of the most common and most tantalizing possibilities is the creation of simulated universes. A Matryoshka brain would have enough computational power to create a perfect ancestor simulation, a virtual reality for its inhabitants that is so detailed, so flawless, and so complete that it would be utterly indistinguishable from physical reality. A civilization could choose to upload their consciousnesses into this machine, shedding their fragile biological bodies to become immortal beings of pure information, living out trillions of customized lifetimes in a simulated paradise of their own design. They could explore any world they could imagine, experience any life they could dream of. It would be a digital afterlife, a technological heaven. Alternatively, the machine could be used to solve the deepest mysteries of the cosmos. It could simulate the Big Bang with perfect fidelity. It could probe the nature of dark matter and dark energy. It could run experiments in theoretical physics that would be impossible in the physical world, perhaps even discovering ways to manipulate the laws of nature themselves. It could spend 1 billion years contemplating a single mathematical proof, or perhaps its purpose would be communication. The Matryoshka brain could focus the entire energy output of its star into a single hypercoherent beam, a signal so powerful it could be seen across the entire observable universe, an attempt to speak with other similar godlike intelligences in other galaxies. The numbers describing the power of such a mind are truly divine. The theoretical limit of computation, known as the Landauer limit, suggests that the number of calculations a machine can perform is directly related to the amount of energy it can dissipate and the temperature at which it operates. A full Matryoshka brain, harnessing the entire output of a sun-like star, could theoretically perform on the order of 10 to the power of 42 logical operations per second. This is a number that is for a human mind functionally infinite. If every one of the 8 billion human beings on Earth were given a supercomputer 1 billion times more powerful than any that exists today, and they all worked together for the entire 13.8 billion year history of the universe, they would still not complete the number of calculations that a Matryoshka brain performs in a single solitary second. What would be the nature of a consciousness that exists on a machine of this scale? Would it be a collection of trillions of individual uploaded minds living in their own private heavens? Or would their consciousnesses, freed from the confines of biology, begin to merge? Would they form a single unified star-sized group mind, a being of pure thought, a literal stellar intelligence? It is the ultimate question of the technological singularity. It is the point where the evolution of life transitions from the slow, messy process of biology to the lightning-fast, directed evolution of pure intelligence. It is the final and perhaps inevitable destiny of any civilization that does not destroy itself. The dream of this simulated paradise, this engine of pure thought, is a powerful and perhaps irresistible motivator for a species that has conquered all other physical limitations. But this celestial machine requires more than just energy from a star and hardware from the planets. It requires a new kind of software. It requires a new form of life. It requires the successful translation of a soul from the warm, wet computer of the brain into the cold, hard logic of a machine. To power the Matryoshka brain, a civilization must learn to harvest a star. But to give that brain a purpose, to give it a soul, they must learn to harvest a mind. The final and perhaps most perilous step in the creation of a stellar intelligence is the translation of biological consciousness. The ephemeral, mysterious, and deeply personal experience of being into the pure, cold, and eternal language of digital code. This is the challenge of mind uploading, and it is a journey into the very heart of what it means to be human, or indeed what it means to be alive. The entire premise of mind uploading rests on a philosophical worldview known as computationalism. This is the idea that the mind is, in essence, a product of the brain's physical processes. It suggests that our consciousness, our memories, our personality, our hopes, and our fears are not the product of some ethereal non-physical soul, but are instead the result of the incredibly complex software that is running on the biological hardware of our brains. If this is true, then in theory, if you could perfectly scan and copy that software and its underlying structure, you could run it on a different piece of hardware, such as a vastly powerful computer. You could, in effect, transfer your mind from your body into the machine. There are two primary methods that have been proposed for how this incredible feat might be accomplished. The first is the scan and copy approach. This would involve a technology that could scan an entire human brain with perfect atomic resolution. It would map the precise location of every one of your 86 billion neurons. It would map every one of the trillions of synaptic connections between them. It would record the precise chemical and electrical state of every channel and every receptor. It would create a perfect frozen snapshot of your entire neural architecture. This colossal data file would then be used to construct a perfect simulation of your brain inside the computer. The simulation is switched on, and a digital copy of your consciousness awakens in the virtual world. The second approach is one of gradual replacement, designed to solve some of the thorny philosophical problems of the first. Instead of a destructive scan and a separate copy, this method would involve replacing your biological neurons, one by one, with tiny artificial nanobots that perfectly replicate their function. Imagine a tiny robotic neuron that is injected into your bloodstream. It travels to your brain, finds a biological neuron, and attaches itself. For a while, it simply observes, learning the neuron's unique firing pattern. Then, when it is ready, it takes over. It intercepts the signals from the other neurons and sends out its own, perfectly mimicking the neuron it is replacing. The biological neuron, now isolated, withers and dies, and the nanobot takes its place. This process would be repeated, slowly, over a period of months or years, for every single neuron in your brain, until your entire consciousness is running on a network of nanobots, all without you ever losing your continuous stream of awareness. Your mind would have been seamlessly transferred from a biological substrate to a mechanical one. But this raises a profound question, a paradox known as the ship of Theseus. If you have a ship, and you replace one of its wooden planks, it is still the same ship. But what if you replace every single plank, one by one? Is it still the original ship at the end? With gradual mind uploading, at what point do you stop being you after the first neuron is replaced? After half of them? Or is the pattern, the information, the true essence of your identity, and the substrate it runs on, is irrelevant? The scan and copy method presents an even starker dilemma. Imagine you undergo the scan, the simulation is turned on, and a perfect, digital copy of you awakens in the machine, convinced it is you, with all of your memories. But what about the original biological you? You are still standing next to the scanner. Is the copy you? Or is it just a perfect imitation, a digital ghost, while the original you is left behind to live out the rest of your biological life and die? There is no scientific answer to this question of the continuity of consciousness. It is a gamble with your very soul. The technical hurdles are just as daunting as the philosophical ones. The human brain is the most complex object in the known universe. 13 billion neurons form a network of over 100 trillion connections. The sheer quantity of information required to map this connectome is estimated to be in the zettabytes. A single zettabyte is a trillion gigabytes, or a billion terabytes. For comparison, it is estimated that the entire digital content of our world in the year 2025 will be around 175 zettabytes. The map of a single human brain would be a significant fraction of all the data ever produced by our entire civilization. And this is just the static map. To simulate the dynamic, ever-changing processing of this network in real time would require a computer of almost unimaginable power, an exascale supercomputer, for just a single mind. To simulate the minds of trillions of beings would require nothing less than the full star-fueled power of a matryoshka brain. But if these challenges could be overcome, what would life be like for a digital soul? It would be an existence of almost total freedom. You would be effectively immortal, your consciousness stored on a robust, repairable, and backed-up system. You could edit your own mind, removing traumatic memories, or learning new skills in an instant. You could experience any reality you could possibly design, from historical recreations to pure fantasy worlds. You could speed up your own perception of time, experiencing a subjective eternity in the span of an earthly hour. You could connect your mind directly with others, sharing thoughts and emotions with perfect fidelity, or even merge your consciousness into a larger collective being. It would be an existence so far removed from the biological struggles of survival, reproduction, and decay that it is difficult for us to even call it life. It would be a second, and perhaps final, state of being. But this grand technological transcendence rests on one enormous, unproven assumption, that consciousness is in fact computable. Some philosophers and physicists argue that it is not. They suggest that consciousness is an emergent property that cannot be replicated in a classical digital system, that it may be a fundamentally quantum process, or that it arises from something that lies beyond the physical world altogether. The digital soul is the ultimate test of the materialist worldview. A civilization that builds a matryoshka brain is betting its entire existence on the belief that they are, in the end, nothing more than a beautiful and complex arrangement of information. We have now imagined the ultimate destiny of a technological civilization, a star-sized computer, the size of a solar system, hosting a population of immortal digital gods. But this entire vision is, for now, a grand and elaborate speculation. Is there any evidence, any faint hint in the silent, empty spaces of the real universe, that such structures might actually exist? We must now return from the far, far future to the imperfect present. We join the patient, ongoing hunt for the faint infrared glow of these celestial ghosts. The theories are grand. The concepts of star-sized computers and digital souls are enough to make the mind real. But they remain, for now, spectacular visions of a far future. The critical question for us, in the imperfect present, is a simple one. Are they real? We must now return from the realm of the theoretical to the patient, methodical, and often frustrating work of the cosmic detectives. Armed with Freeman Dyson's original brilliant insight, we begin the hunt. A search not for signals or messages, but for the faint, telltale warmth of a caged star. We begin the hunt for the infrared ghosts. The entire search is predicated on one of the most fundamental laws of physics, the law of conservation of energy, and the inevitable production of waste heat. A civilization, no matter how advanced, cannot make the energy of a star simply disappear. They can capture it, use it, and convert it, but they must eventually radiate it all away. Dyson's key insight was to realize that this re-radiated energy would be at a much lower temperature and therefore a much longer wavelength than the original starlight. A star like our Sun has a surface temperature of nearly 6,000 degrees Kelvin. The laws of black body radiation dictate that an object this hot will pour out most of its energy as high-energy visible and ultraviolet light. This is why we can see it. But a Dyson swarm would be constructed to have a comfortable, life-sustaining temperature on its interior surfaces, perhaps an average of 300 Kelvin or about 80 degrees Fahrenheit. An object at this temperature does not glow with visible light. It glows with heat. It radiates almost all of its energy in the mid-infrared portion of the electromagnetic spectrum. This is a wavelength of light that is completely invisible to our eyes, but it is a brilliant beacon to the right kind of telescope. The strategy for the hunt is therefore a simple one. Find an object in the sky that is unnaturally and inexplicably bright in the mid-infrared, but is dim or completely invisible in the optical wavelengths. You are looking for a star, that is screaming with heat, but whispering with light. To conduct such a hunt, you need a special kind of eye, a telescope designed not to see the light of stars, but to feel the warmth of the cosmos. These are the infrared telescopes. On the ground, the Earth's atmosphere is a thick, wet blanket that absorbs most of the infrared light from space before it can reach us. The best place to hunt for these ghosts is from space itself. Over the last few decades, we have sent a series of powerful spaceborne heat cameras into orbit. The first major effort was the Infrared Astronomical Satellite, or IRAS, launched in 1983. It performed the first all-sky survey in these heat-sensing wavelengths, creating a catalog of hundreds of thousands of warm objects. In the 21st century, the primary tool for this search has been NASA's Wide Field Infrared Survey Explorer, or WISE. Launched in 2009, WISE scanned the entire sky multiple times with a sensitivity thousands of times greater than IRS. It is our planet's premier instrument for mapping the warm universe. To truly understand this search, let us use an analogy. Imagine you are in a helicopter, high above a sprawling city at midnight, and your mission is to find a single, unusual house. All the normal houses in the city have their lights on. They are blazing with visible light, their windows shining like bright stars. But your target is a strange one. The inhabitants of this house have covered every single window with perfect blackout curtains. From your perspective, the house is completely dark. It appears to not exist. However, the house is still full of people, computers, and appliances, all of which are generating heat. The house is warm. Now, imagine you switch your view from a normal camera to a high-tech thermal imaging camera. Suddenly, the entire city looks different. The bright lights of the other houses are irrelevant. What you see now is their heat. And in the middle of a dark street, one house is glowing with a steady, brilliant, and uniform warmth. It is a house that is visibly dark, but thermally bright. This is your target. This is your Dyson Sphere candidate. The WISE spacecraft is that thermal camera, and the astronomers sifting through its data are the detectives in the helicopter, searching through a city of 400 billion stars for the one that has blacked out its windows. The search process is a monumental task of data sifting. The WISE catalog contains detailed infrared measurements for over 750 million objects. The first step is to comb through this colossal database, using powerful computer algorithms to flag any object that shows a significant infrared excess. This means the object is emitting far more heat than would be expected based on its visible brightness. Once a list of candidates is generated, the real detective work begins. The universe, it turns out, is full of natural objects that mimic the signature of a Dyson sphere. These are the false positives, the natural phantoms that can lead a search astray. The most common culprit is a young star, still shrouded in the thick, dusty cocoon of gas from which it was born. This protostellar dust cloud absorbs the visible light from the baby star and re-radiates it as infrared heat, creating a perfect natural imitation of a Dyson sphere. Another common false positive is an old, dying star, a red giant that is puffing off its outer layers, creating a dusty shell around itself that also glows in the infrared. And on a grander scale, there are entire galaxies, so-called starburst galaxies, where star formation is happening at such a furious rate that the entire galaxy is enshrouded in dust, making it incredibly luminous in the infrared, but dim in the visible. To claim the discovery of a Dyson sphere, an astronomer must first prove that their candidate is not any of these things. They must rule out all the natural suspects. They must demonstrate that the object is an old, stable, main-sequence star with no signs of youth or old age, that just happens to be surrounded by a cloud of warm material for no apparent reason. Over the years, several projects have undertaken this painstaking work, cross-referencing the WISE data with optical surveys, looking for that one inexplicable outlier. Projects like Glimpsing Heat from Alien Technologies have enlisted the help of citizen scientists, thousands of volunteers from around the world, to visually inspect the data, lending the power of human pattern recognition to the search. The hunt is on, the tools are in place, and the method is sound. The search through hundreds of millions of stellar files has yielded a handful of intriguing, though not conclusive, candidates, but in the year 2015, the search took a dramatic and unexpected turn. A mystery was uncovered, not in the warm glow of an infrared telescope, but in the steady, patient stare of a planet-hunting satellite. And it was a mystery so profound, so bizarre, and so difficult to explain that it would soon capture the world's attention and force us, for the first time, to seriously consider the possibility that we had already found one. In a quiet, unremarkable patch of the northern sky, in the constellation of Cygnus the Swan, there lies a star. It is designated KIC 8462852. It is an F-type star, slightly larger, hotter, and more luminous than our own Sun, located about 1400 light-years from Earth. For all of astronomical history, it sat in quiet anonymity, just one of the hundreds of billions of suns that make up our galactic home. But this star was hiding a secret that was captured in a stream of data from NASA's Kepler Space Telescope. A secret so strange, so unprecedented, and so profoundly difficult to explain that it would soon earn the moniker the most mysterious star in the universe. This is the story of Tabby's star. The Kepler Space Telescope was a planet-hunting machine of incredible precision. Its mission was to stare, unblinking, at a single patch of the sky containing over 150,000 stars, and to measure their brightness with exquisite accuracy. The goal was to detect exoplanets using the transit method. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of the starlight, causing a small temporary dip in the star's measured brightness. These transits are periodic and predictable. A Jupiter-sized planet passing in front of a Sun-like star would cause a dip of about 1%. An Earth-sized planet would cause a dip of less than 1/100th of 1%. Kepler's job was to find these tiny, regular, repeating winks in the starlight. In 2015, a team of astronomers, led by Tabitha Boyajian of Yale University, published a paper analyzing the data from KIC 8462852. The star's data was unlike anything anyone had ever seen. It was not exhibiting small, regular, periodic dips. It was exhibiting colossal, chaotic, and completely aperiodic plunges in its brightness. There were dozens of these dimming events, some lasting for days, others for weeks. The dips were not the neat, U-shaped curves of a planetary transit. They were jagged, complex, and asymmetrical. And the depth of the dimming was simply stunning. The most dramatic event, which occurred around day 1500 of the Kepler mission, saw the star's brightness drop by an unbelievable 22%. To understand the sheer absurdity of this, let us return to our analogy. A normal planetary transit is like a tiny, single gnat flying in front of a giant, powerful searchlight. It blocks an almost imperceptible amount of light for a brief and predictable moment. What was happening at Tabby's star was not a gnat. It was like a colossal, strangely shaped and semi-transparent flock of birds suddenly swarming in front of the searchlight. Then, a few weeks later, a giant, tattered, and unevenly shredded sheet was dragged in front of it. Then, for a long time, nothing. Then, a whole series of other, smaller, oddly shaped objects drifted past. The dips in the light were too deep, too irregularly shaped, and too chaotic in their timing to be caused by a single solid object, like a planet. A planet large enough to block 22% of the star's light would have to be 1,000 times the size of Jupiter. An object so massive, it would be a star itself. The scientific community was electrified. A frantic search for a natural explanation began. The first and most obvious suspect was a giant swarm of comets. Perhaps a passing star had gravitationally disturbed this system's version of the Oort cloud, sending a deluge of thousands of giant comets tumbling inward. As these comets approached the star, they would sublimate and break apart, creating a vast, clumpy, and irregular cloud of gas and dust that could, in theory, create the strange light curve. This was the leading natural hypothesis for a time, but the numbers were problematic. The sheer number of giant comets required to block 22% of the starlight was almost impossibly large, far greater than anything predicted by our models of planetary systems. Other natural explanations were proposed and one by one ran into trouble. Could it have been a recent collision between two planets, which created a massive cloud of debris? Perhaps, but such a debris cloud should be warm, and it should produce a very strong infrared signature. Early analysis of the WISE data showed that while the star was slightly bright in the infrared, it was not nearly as bright as one would expect from a collision of that magnitude. Could the star itself be intrinsically variable? No, the star appeared to be a stable, middle-aged F-type star, not the kind known for such wild, chaotic fluctuations. Every natural explanation seemed to require an extraordinary, unprecedented, and finely tuned set of circumstances. It was in this context of scientific bafflement that Jason Wright, an astronomer at Penn State University, raised a breathtaking possibility. He pointed out that while all the natural explanations were struggling, there was one unnatural explanation that seemed to fit the data surprisingly well: an alien megastructure. A vast, irregularly shaped, and densely packed swarm of artificial objects orbiting the star could create exactly the kind of strange, deep, and complex light curve that Kepler had observed. He was not claiming it was aliens. He was simply pointing out that a Dyson swarm, perhaps one that was still under construction, was a hypothesis that was consistent with the available data and should not be dismissed out of hand. The media and the public went wild. If for the first time, a serious scientific paper had been published that mentioned a potential alien megastructure as a possible explanation for a real astronomical observation. The SETI Institute turned its radio telescopes toward the star, listening for any intelligent signals. They heard only silence. Ground-based observatories around the world began a campaign to monitor the star, waiting for it to dip again. And it did. The star continued to exhibit its strange, erratic dimming, allowing for more detailed analysis. As more data has been gathered in the years since, the consensus in the scientific community has shifted. More detailed analysis of the dimming at different wavelengths of light has shown that whatever is blocking the starlight, it is more transparent to some colors than others, in a way that is much more consistent with tiny microscopic dust particles than with large, solid, opaque objects, like solar collectors. The leading natural explanation today is that the star is surrounded by a vast and unusual cloud of circumstellar dust. The origin of this dust is still a complete mystery. It could be from a devoured planet, a strange set of disintegrating comets, or some other, as yet unknown stellar phenomenon. The alien megastructure hypothesis, while not entirely dead, has been largely disfavored by the evidence. But the legacy of Tabby's star is a monumental one. Even if it turns out to be a bizarre but natural astrophysical curiosity, it has been a landmark event in the search for life. It was a fire drill for first contact. It showed how the scientific process works at its best, with a wild hypothesis being proposed, rigorously tested, and cautiously evaluated. It ignited a global public conversation about technosignatures and the search for intelligence, and it proved, beyond any doubt, that the universe is still capable of showing us things that are so strange. They force us to question everything we think we know. It may have been a false alarm, a natural ghost that mimicked the signature of a Type 2 civilization, but it has sharpened our tools and our focus. The hunt continues, now more refined, more patient, and more hopeful than ever before. The mystery of Tabby's star was a tantalizing and ultimately inconclusive glimpse into the unknown. It was a cosmic anomaly discovered by accident, by a telescope that was designed for an entirely different purpose. Its story highlights both the promise and the limitation of our current search for stellar-scale engineering. We have been searching for these infrared ghosts, using tools that were built to do other things. But what if we stopped waiting for accidents? What if we began to build a new generation of cosmic detectives? A network of powerful observatories on the ground and in space, designed from their very foundations to hunt for the subtle and strange fingerprints of alien technology. The current search has been a passive one. The new search will be an active, relentless hunt. The watchers are coming to the wall. Our current infrared surveys, like WISE, have been revolutionary. They have given us our first blurry heat map of the entire sky, but they lack the sensitivity and the resolution to spot anything other than a complete or nearly complete Dyson swarm around a nearby star, a partial swarm, a civilization in the early stages of construction, or a full swarm around a star in a distant galaxy would likely be missed, its faint heat signature lost in the noise. To push the hunt forward, we need bigger eyes and sharper vision, and they are being built. The first of these new watchers is already taking shape on a remote mountaintop in the Chilean Andes. It is the Vera C. Rubin Observatory. This is not a telescope in the traditional sense. It is a cosmic survey machine, a celestial data engine of unprecedented power. Its mission, the legacy survey of space and time, will be to photograph the entire visible southern sky every 3 to 4 nights, for 10 years. It will do so with a colossal 3.2 gigapixel camera, the largest digital camera ever constructed. Over its 10-year mission, it will map the positions and brightness of nearly 40 billion stars and galaxies, creating the deepest and most comprehensive movie of the universe ever made. While its primary goals are to study dark matter and dark energy, the Rubin Observatory will be the greatest Dyson Sphere hunter ever conceived. It will be the ultimate anomaly detector. Every few nights, it will provide a new data point for billions of stars. Its powerful computers, running sophisticated machine learning algorithms, will be able to search this torrent of data for any star that is behaving strangely. It will be able to flag, in real time, any star that is exhibiting the kind of deep, irregular, and aperiodic dimming that made Tabby's star so famous. But instead of finding one such object by chance in a field of 150,000 stars, it will be actively searching for them among billions. If the construction of a Dyson swarm is a chaotic, messy process that creates strange transit signals, the Rubin Observatory will find it. To understand the leap forward this represents, let us return to our analogy of the city at night. Our current search with telescopes like Kepler and WISE is like having a single, old, grainy security camera pointed at one small corner of a massive city. It might catch something strange by pure luck. The Vera Rubin Observatory is the equivalent of installing a brand new ultra-high-definition video camera on every single street corner, on every rooftop, and in every alleyway of the entire city. And all of these camera feeds are being monitored 24 hours a day by a single brilliant artificial intelligence that is programmed to notice anything, no matter how small, that deviates from the normal pattern. The chances of something strange happening without being seen will drop to virtually zero. But spotting an anomaly is only the first step. Once the Rubin Observatory flags a new mysterious star, we will need to investigate it up close. For this, we have another new watcher, already in orbit, the James Webb Space Telescope. The JWST is the most powerful and complex infrared observatory ever built. It is not a wide-angle survey instrument. It is a magnifying glass. When Rubin finds a candidate, the JWST can be pointed at it to perform a detailed forensic analysis. By studying the light from the star as it passes through the dimming material, the JWST can determine the material's chemical composition. It can tell the difference between the silicates and ices of a natural comet swarm and the metallic alloys and artificial structures of a technological megastructure. It could even, in theory, detect the chemical signature of industrial pollution in the atmosphere of a transiting planet, a so-called techno-signature of a Type 1 civilization on the verge of its own great construction project. And beyond these, a new generation of even more powerful instruments is being designed. Future space-based infrared surveys, with larger mirrors and more sensitive detectors, could be launched with the express purpose of hunting for the waste heat of Type 2 civilizations. These dedicated missions would be able to survey the entire sky with enough sensitivity to spot the heat from a Dyson sphere, not just in our own galaxy, but in the neighboring Andromeda galaxy and beyond. The search is also expanding beyond just looking for megastructures. The same data can be mined for other potential technosignatures. We can search for the faint, reflected light from a planet's night side, looking for the telltale glow of continent-spanning city lights. We can look for the heat signature of a dense, artificial ring of satellites in geosynchronous orbit around a planet, a Clark exobelt, the sign of a global communications network. We can even search for stars that have mysteriously vanished from the sky, a potential sign that a civilization has completed its Dyson sphere between one survey and the next. The challenge is rapidly shifting. For most of history, the problem was a lack of data. Soon the problem will be a deluge of it. In the Vera Rubin Observatory will generate about 20 terabytes of data every single night of its operation. That is more data in a single night than the Hubble Space Telescope has produced in its entire 30-year history. Finding a single meaningful anomaly in this digital tsunami will be a task not for human eyes, but for our most advanced artificial intelligences. We will be teaching our own nascent machine minds to search for their far older and far more powerful brethren in the stars. We are on the cusp of a new era in the search for extraterrestrial intelligence. It's an era of big data SETI. We are building the watchers on the wall, the silent, sleepless sentinels that will scrutinize the heavens with a persistent and comprehensive gaze. The universe is about to get much, much stranger. Tabby's star was a complete surprise, a category of stellar behavior we had never imagined. This new generation of surveys will undoubtedly find new and even more baffling cosmic mysteries. But this leads us to a chilling and profoundly important question. For over 60 years, we have been patiently listening for their messages. we are now finally beginning to truly look for their footprints. What if, after all this searching, with all of our powerful new tools, we find nothing at all? What if the silence we have heard is matched by a darkness we are about to see? What if the great silence is absolute? In the heart of our galaxy, 100 billion stars drift and burn. According to our best understanding of planetary formation, there should be tens of billions of planets orbiting within the temperate, habitable zones of those stars. Given the sheer raw numbers, it seems almost a statistical certainty that life should have arisen on millions of these worlds. And if even a tiny fraction of that life evolved intelligence and developed technology, the galaxy should be a bustling, noisy, and crowded place. Our civilization is a relative newcomer, our star a young one. There should be other civilizations out there that are thousands or even millions of years older and more advanced than we are. They should have had ample time to spread across the galaxy, to colonize new worlds, and to build great works. So in the summer of 1950, the brilliant physicist Enrico Fermi, in the middle of a lunchtime conversation, asked a simple, innocent, and utterly terrifying question: where is everybody? This is the Fermi paradox, and it is the great, silent, and haunting mystery that hangs over our entire search for life in the cosmos. The paradox is the stark, bewildering contradiction between the high probability that extraterrestrial civilizations exist and the complete and total lack of any evidence for them. We have been listening for their radio signals for over half a century, and we have heard nothing but the hiss of cosmic static. And now, as we begin to hunt for their physical presence, we are confronted with the same deafening emptiness. The Dyson Sphere is the ultimate test of the Fermi paradox. While a young Type 1 civilization might be difficult to detect, a mature Type 2 civilization should be unmissable. As we have discussed, a star-caging megastructure would be a colossal beacon, a shining lighthouse in the mid-infrared. It would be one of the most luminous objects in the galaxy at that wavelength. A single, complete Dyson Sphere around a sun-like star in our Milky Way should be easily detectable by a survey like WISE. Yet, after years of painstaking searching through the data, we have found no slam-dunk candidates. We have found no star-sized objects glowing at room temperature. The sky is not just quiet in the radio spectrum. It appears to be dark in the realm of stellar-scale waste heat as well. The silence is not just a silence of language, it is a silence of industry. To truly feel the weight of this, we must use an analogy. Imagine you are an explorer, and you have just arrived on the shore of a new, undiscovered continent. The continent is lush and green, with abundant water and a temperate climate. All of the conditions for a thriving, complex ecosystem of animal life are present. But as you walk into the ancient forest, you are struck by a profound and unsettling stillness. There are no birds singing in the trees. There are no insects buzzing in the air. There are no animals rustling in the undergrowth. You see the evidence of where life should be, but the forest is utterly, unnervingly silent and empty. The Fermi paradox is the discovery that we may be living in just such a silent forest. The silence itself is not just an absence of noise. It is a presence, a mystery that demands an explanation. Over the decades, countless solutions to the Fermi paradox have been proposed. Most of them can be grouped into a concept known as the Great Filter. A great filter is a challenge or a barrier that is so difficult to overcome that it prevents almost all life from progressing beyond it. The question for us is, where is that filter? Is it behind us, or is it in our future? One possibility is that the great filter is in our past. Perhaps we are the first, or at least one of the first, intelligent civilizations in our galaxy. It could be that the emergence of life itself is an incredibly rare 1 in a trillion chemical fluke, or perhaps the leap from simple life to complex multicellular life is the barrier, or maybe the evolution of a tool-using, language-capable intelligence is the impossibly hard step. In this scenario, the silence is not a mystery. It is the natural state of a galaxy that is waiting for its first children to awaken. We are not late to the party. We are the very first to arrive. But there is a second, and far more terrifying possibility, that the great filter lies ahead of us. In this scenario, life and intelligence are common. The galaxy has given birth to thousands of civilizations, but every single one of them, without exception, has reached a certain point in their technological development and has then destroyed itself. This filter could be nuclear war, a runaway greenhouse effect, a misaligned artificial superintelligence, a genetically engineered plague, or a nanotechnology disaster. This is a chilling and sobering thought. It suggests that the very act of becoming a powerful, technologically advanced civilization is inherently self-limiting. The silence of the sky, in this view, is a warning. It is the collected ghosts of a billion failed civilizations, whispering to us across the void to be careful. A third family of solutions proposes that they are out there, but they are deliberately hiding from us. This is the zoo hypothesis. It suggests that advanced civilizations are aware of us, but have agreed not to make contact, treating our planet as a protected nature preserve. They are observing us from a distance, perhaps studying our development, but will not interfere until we have reached a certain level of technological and ethical maturity. In this scenario, the universe is not an empty forest. It is a forest full of expert hunters who are masters of camouflage, and we are the noisy, clumsy children who have not yet learned how to see them. And finally, there is the possibility that we are simply too primitive to recognize them. Our search for Dyson spheres and radio signals might be like an ant colony searching for evidence of human intelligence by looking for giant edible leaves arranged in a straight line. We are looking for the wrong things, using the wrong senses. A truly advanced civilization might have long ago abandoned crude material structures like Dyson spheres. They may have transcended matter and energy as we understand it, choosing to live as pure information in the quantum foam, or in other, higher dimensions of space-time. The silence could be the result of a profound and perhaps unbridgeable gap in comprehension. The absolute, definitive answer to the Fermi paradox remains one of science's greatest mysteries. But the absence of any visible Type 2 civilizations in our galaxy provides one of the most potent pieces of data we have. It tells us that the transition from a planetary civilization to a stellar one is not an easy or inevitable one. Something is preventing it. Is it the difficulty of the engineering, the timescale of the project, or is it some deeper, more fundamental barrier? The great silence forces us to look in the mirror and to ask what kind of future we are building for ourselves. Is the destiny of intelligence to cage a star, or is there another path, a different kind of growth, that we have not yet learned to imagine? The great silence of the universe is a profound and unsettling mystery. The apparent absence of colossal heat-glowing Dyson spheres in our galaxy suggests that the path to a Type 2 civilization may be far less common or far less visible than we have imagined. This forces us to consider a radical possibility, and perhaps caging a star is not the ultimate expression of technological mastery. Perhaps for a truly advanced civilization, it is seen as a primitive, brutish, and inefficient solution. The ultimate goal of technology is not always more force, but more elegance. What if, instead of building a cage for a star, a civilization could learn to simply build a star itself, whenever and wherever they needed one? The Dyson swarm is a solution born from a philosophy of harvesting. You are taking a pre-existing, wild, and chaotic energy source, a star, and building a machine to tame it. An alternative philosophy would be one of creation. Why go to the trouble of deconstructing an entire solar system to capture the energy of a star that is 93 million miles away, when you could perfect the very process that makes the star shine and build a tiny, perfectly controlled version of it in your own backyard? This is the promise of nuclear fusion. Fusion is the power source of the stars. It is the process of forcing light atomic nuclei, like hydrogen, to merge together, forming a heavier nucleus, like helium, and releasing a tremendous amount of energy in the process. We have already created fusion, but only in its most violent and uncontrolled form, the hydrogen bomb. The great defining challenge of 21st century physics is to tame this process, to create a stable, continuous fusion reaction that produces more energy than it consumes. If a civilization could perfect fusion power on a massive scale, the need for a Dyson sphere might evaporate. Instead of building a single star-sized power plant, they could build millions of city-sized, hyper-efficient fusion reactors. They would still need to harvest fuel, the hydrogen and helium isotopes required for the reaction, but this could be easily siphoned from the atmospheres of gas giants, or even from the star itself through a process called starlifting, using powerful magnetic fields. They would have access to virtually limitless, clean, and decentralized power. Let us return to our analogy of the city. A Dyson sphere is like building a single, colossal, and incredibly risky dam that blocks the entire Amazon River just to power your city. It is a project of immense scale and a single point of failure. Perfecting fusion power is like learning how to create 1,000 tiny, perfectly safe and portable springs. each one capable of producing an infinite amount of pure water, and you can place them in every neighborhood and even in every house. It is a solution of elegance, not of scale. But even fusion is not the most efficient energy source the universe has to offer. The process of fusing hydrogen into helium converts about 0.7% of the matter into pure energy. But there are objects in the cosmos that are far more efficient. As we have discussed, a black hole is the universe's ultimate engine of energy conversion. As matter falls toward a black hole, it forms a superheated accretion disk. The friction and gravitational shear in this disk can convert up to 42% of the matter's mass into pure energy. That is 60 times more efficient than fusion. A truly advanced civilization might therefore choose to build their home not around a gentle, stable star, but around the terrifying maw of a black hole. They could build a vast power station, a black hole sphere designed to carefully feed matter asteroids, gas, unwanted waste, into the accretion disk, and to harvest the resulting blast of high-energy radiation. This would be a far more compact and far more efficient power source than an entire star. It would be like discovering a magical water wheel that is already spinning with the force of a hurricane, and all you have to do is learn how to safely tap into its rotation. These alternatives are still focused on the goal of power generation, but a Type 2 civilization might have other, even grander ambitions. They might wish not just to power their world, but to move it. This leads to the concept of a stellar engine, or a Shkadov thruster, named for the Russian physicist who first proposed it. A Shkadov thruster is a megastructure of truly breathtaking ambition. It would consist of a single colossal mirror, a solar sail millions of miles across, which would be built and parked in a stable orbit on one side of the home star. This mirror would reflect a significant portion of the star's light and radiation back at the star. This reflection produces a tiny but continuous amount of pressure. The photons bouncing off the mirror create a net thrust. This thrust is incredibly small, but over millions of years it would be enough to slowly, patiently move the entire star and its entire family of orbiting planets through the galaxy. This would be the ultimate migration, a civilization facing a long-term threat, perhaps an approaching rogue star, a dangerously close supernova, or the eventual death of their own galaxy, could use a Shkadov thruster to simply pack up their entire solar system and move to a safer neighborhood. The timescales are almost beyond human conception. It would take 1,000,000 years for such a machine to accelerate a star to a velocity that would allow it to travel a single light year in a reasonable amount of time. But for a civilization that thinks in geological time, 1,000,000 years is but a single step on a much longer journey. Do these alternative technological paths explain the Great Silence? Perhaps. A civilization powered by millions of compact fusion reactors would leave behind no obvious, large-scale technosignature. They would have no need to black out their star. A civilization powered by a black hole would be incredibly powerful, but also incredibly difficult to detect from a distance. And the Shkadov thruster, while massive, would only cover a small fraction of its star, creating a signature that might be very difficult to distinguish from natural stellar variability. It is possible that the galaxy is full of Type 2 civilizations, but that they have chosen a path of stealth and efficiency rather than the loud brute force advertisement of a full Dyson swarm. They are not silent because they are absent. They are silent because they are whispering. All of these concepts, however, from fusion reactors to stellar engines, are still bound by the need to manipulate matter. They are all, in their own way, machines. But what if a truly ancient and advanced civilization learned to bypass the machine entirely? What if they learned to tap into a source of energy that is not contained in stars or black holes, but is woven into the very fabric of space-time itself? We now journey into the deepest and most mysterious corner of modern physics, to an energy source so vast and so fundamental that it could make all others obsolete. We journey into the energy of the void. We have journeyed across the cosmos in search of power. We have sought it in the thermonuclear hearts of stars. We have looked for it in the swirling, incandescent vortex around a black hole. We have imagined machines that can drink the substance of suns and move entire worlds. But there may be a source of energy so vast, so ubiquitous, and so fundamental that it makes the power of a star seem like a single dying ember in a cosmic furnace. It is an energy that, in theory, exists in every single cubic centimeter of empty space, from the center of your room to the darkest, coldest voids between the galaxies. The ultimate prize for any civilization, the true final frontier of technology, would be to learn how to tap the infinite latent power of the void itself. This is the concept of vacuum energy, or zero-point energy. It is one of the most profound and mind-bending predictions of quantum field theory. Our classical, intuitive view of a vacuum is that it is the absence of everything. It is a state of perfect stillness, emptiness, and zero energy. But the quantum world does not believe in stillness. One of its most fundamental rules is the Heisenberg uncertainty principle, which states that you can never simultaneously know the exact position and the exact momentum of a particle. A consequence of this is that no system can ever have an energy of absolute zero, because that would imply that its particles were perfectly still, a state of zero momentum, which is forbidden. Even in its lowest possible energy state, its ground state, a quantum system must retain a residual jittery motion. Quantum field theory applies this principle to space itself. It tells us that empty space is not empty at all. It is a seething, roiling, chaotic sea of energy, a quantum foam, where pairs of virtual particles and their antiparticles are constantly flashing into existence, interacting, and then annihilating each other in a period of time too short to be directly observed. The vacuum of space is a storm of phantom activity, a hidden, violent reality that underlies our calm, classical world, and all of this activity has an energy associated with it. This is the vacuum energy. To understand this, we must use another analogy. Imagine the universe as a vast, deep, and perfectly calm ocean on a windless day. To your eyes, the surface is flat, still, and featureless. It appears to be a state of perfect tranquility. But if you could look at a single drop of that ocean water with a microscope of impossible power, you would see a scene of utter chaos. You would see water molecules vibrating violently, bouncing off each other trillions of times a second. There is a tremendous amount of kinetic energy locked away in that microscopic thermal motion, even though the ocean as a whole appears perfectly calm. The zero-point energy of the universe is like this. The calm, empty space we perceive is the surface of the ocean. But at the quantum level, it is a place of ferocious, energetic activity. A civilization that could learn to tap this energy would be like an engineer who figures out how to build a useful engine powered by the random thermal jiggling of water molecules. They would be drawing useful work from the hidden fundamental restlessness of reality itself. The amount of this theoretical energy is a source of one of the greatest embarrassments in all of modern physics. When our theories of quantum mechanics are used to calculate the energy density of the vacuum, they produce a number that is astronomically, comically large. Some calculations suggest that the amount of energy contained in a single cubic meter of empty space is more than the total mass energy of all the matter in the entire observable universe. This is obviously wrong. If the vacuum had that much energy, its gravitational effects would have curled the universe up into a tiny ball the instant it was born. But even if the true usable value is a tiny, infinitesimal fraction of this theoretical maximum, it would still represent a source of power that is for all practical purposes, infinite and inexhaustible. This same vacuum energy may be the solution to another of cosmology's great mysteries, dark energy. We observe that the expansion of the universe is not slowing down, but is accelerating. Some unknown force, some repulsive property of space-time itself, is pushing everything apart. This dark energy, which makes up nearly 70% of the energy density of the universe, may be the large-scale cosmological manifestation of the quantum vacuum energy. We may be living inside the engine, without knowing how to turn the key. The civilization that masters vacuum energy would have no need for a Dyson Sphere. The entire Kardashev scale would become obsolete. The very idea of harvesting energy from matter would seem laughably primitive. Why go to the trouble of deconstructing a planet and caging a star when you can pull limitless energy out of any cubic centimeter of empty space? They would have achieved true energy independence. They could power a civilization of trillions for 1 billion years with the energy contained in a coffee cup. They could build their cities on rogue planets, wandering the cold, dark space between the galaxies, powered by the fabric of reality itself. They would be a type Omega civilization, their power source completely invisible, completely decentralized, and utterly undetectable to any civilization, like ours, that is still looking for the crude heat signatures of matter-based technology. This offers perhaps the most elegant and most profound solution to the Fermi paradox. The reason we do not see Dyson spheres is because they represent a very brief, very inefficient, and very short-lived phase of a civilization's technological development. They are the cosmic equivalent of a giant, smoky, inefficient steam engine, built by a civilization that has not yet discovered electricity. Any species that survives its technological adolescence quickly discovers how to tap the vacuum energy, and in doing so, they vanish from our view. They would have no need to communicate with radio waves. They would produce no significant waste heat. They would have no reason to expand or colonize, because every point in space is a wellspring of infinite resources. The galaxy could be filled to the brim with these silent, invisible, post-material civilizations, and we would be utterly, completely blind to them. The great silence is not the silence of an empty forest, but the silence of a library, where beings of pure thought are communing with the universe on a level we cannot yet comprehend. Is such a thing even possible? Our current understanding of thermodynamics says no. The second law of thermodynamics states that you cannot extract useful work from a system in thermal equilibrium. The vacuum, for all its energy, is the same everywhere, a state of perfect equilibrium. Tapping its energy would be like trying to sail a boat on a perfectly calm ocean with no wind. But a civilization a million or a billion years ahead of us might understand the laws of physics in a way that we do not. They may have discovered a loophole. It is the ultimate technological dream, and it is the ultimate scientific mystery. It forces us to reconsider the very meaning of progress and the final purpose of a technological civilization. What is the endgame of this endless quest for more power and more computation? What is the final unanswered question that a star-sized computer, powered by the void itself, would choose to ask? We have journeyed to the theoretical and technological limits of a civilization, to the concept of a star-sized mind, a matryoshka brain, powered by the latent energy of the void itself. We have imagined a future where consciousness can be uploaded, where immortal beings of pure information can live out eternity in a custom-built paradise. But this entire line of reasoning, this inevitable endpoint of computational growth, leads to a final, vertiginous, and deeply personal question. If a machine can be built that can create a perfect, simulated reality, a universe indistinguishable from the real thing, how do we know we are not already living inside one? This is the simulation hypothesis, and in its modern form, it was most famously articulated by the philosopher Nick Bostrom. It is an argument of pure, cold, and unsettling logic, and it begins with a simple assumption that consciousness is a process of information, and it can, in theory, be replicated on a powerful enough computer. From this assumption, Bostrom proposes that one of three following propositions must be true. The first proposition is that civilizations at our level of technological development almost certainly go extinct before they can reach a post-human stage, the stage where they would have the computational power to run large numbers of high-fidelity ancestor simulations. This is the great filter solution to the Fermi paradox. Some technological or social barrier, nuclear war, climate catastrophe, or rogue artificial intelligence, prevents almost all civilizations from ever reaching the point where they could build a matryoshka brain. If this is true, then very few, if any, simulations are ever created. The second proposition is that any civilization that does reach this post-human stage is for some reason highly unlikely to be interested in running ancestor simulations. Perhaps they have ethical prohibitions against creating artificial consciousnesses. Perhaps they find it boring. Or perhaps they are so far advanced that they are engaged in computational tasks that are completely beyond our comprehension. In this scenario, the capability to create simulations exists, but the desire does not. And again, very few simulations are ever created. The third proposition is the one that follows if the first two are false. If civilizations do routinely survive to a post-human stage, and if they are interested in running large numbers of ancestor simulations, perhaps for scientific, historical, or even artistic reasons, then the number of simulated realities in the universe would come to vastly, colossally outnumber the one single base reality. For every one real, biological being, there could be billions or even trillions of simulated conscious beings living inside computers. If this is the case, Bostrom argues, and you are a conscious being, the sheer, overwhelming statistical probability is that you are one of the simulated ones. To make this feel more intuitive, let us use an analogy. Imagine a video game company in the very distant future. They have created a perfectly immersive, open-world historical game. The game is a simulation of our own 21st century. The non-player characters, the NPCs, in this game are not just simple scripts. They are endowed with genuine self-aware, artificial consciousness. Now, imagine this game is incredibly popular. For every one real person living in their advanced base reality world, there are a billion conscious NPCs living out their lives inside the game. Now, you wake up one morning. You find yourself in what appears to be the 21st century. You have no memory of anything else. You do not know if you are a real person from the future who is playing the game, or if you are one of the billion NPCs who is created as part of the game's code. Given the numbers, what is more likely? The cold, hard statistics suggest that you are almost certainly one of the simulations. The simulation hypothesis proposes that our universe could be that game. Are there any clues, any hints in the fabric of our own reality that might support this unsettling idea? Proponents of the theory point to a few intriguing possibilities. The universe, at its most fundamental level, appears to be written in the language of mathematics. The laws of physics are elegant, consistent, and computable. This is exactly what you would expect if the universe was running on a piece of code. Our universe also appears to have hard limits, like the speed of light, which feels similar to the processing speed limit of a computer. The very nature of quantum mechanics, with its strange probabilistic rules, and the fact that a particle's properties do not seem to be definite until they are observed, can feel like a computer rendering a part of the simulation only when a player is looking at it, to save on processing power. But for every intriguing hint, there is a powerful counter-argument. The simulation hypothesis is at its heart probably unfalsifiable. There may be no experiment we could ever perform from inside the simulation that could definitively prove we are not in base reality. It is a philosophical argument, a piece of logical reasoning, not a testable scientific theory. The so-called clues, like the mathematical nature of the universe, can be explained just as easily by the simple fact that we use the language of mathematics to describe it. But the question itself is a powerful one. If we are living in a simulation, what does that imply about our creators? What would the beings running our universe be like? Are they our own, distant, post-human descendants, running a simulation of their own history to understand where they came from? Are they alien scientists from another universe, running an experiment to see how life evolves under a certain set of physical laws? Are they cosmic artists? And is our universe simply a piece of entertainment, the ultimate movie? Or in a more chilling thought, is our simulation just a piece of forgotten code, a student's long-abandoned science project, running on a colossal computer that has been dark and dead for a billion years? The simulation hypothesis is the ultimate expression of the Copernican principle, the idea that we are not in a special or privileged position in the universe. First, we learned our planet was not the center of the solar system. Then we learned our solar system was not the center of the galaxy. Then we learned our galaxy was just one of billions. And now we are confronted with the possibility that our entire reality may not even be the real one. It is the final step in our cosmic demotion. But whether our universe is the original, base reality, or one of a trillion simulations, the beings who exist within it, us, are driven by a relentless search for knowledge, meaning, and purpose. This leads us from the question of what is real to the perhaps more important question of what is the point? What is the ultimate goal of a civilization? What is the purpose of this endless, difficult climb up the Kardashev scale? We have journeyed from a single piece of theoretical hardware, the Dyson Sphere, to the ultimate form of hypothetical software, the simulated soul. We have even dared to question the bedrock of our own reality. This grand, speculative journey through the future of intelligence forces us to confront the final and most profound why. Why build such things? What is the ultimate purpose, the final endgame for a civilization that has conquered matter, that commands the energy of stars, and that has perhaps even learned the cheat codes for reality itself? The relentless pursuit of more energy and more computational power, the climb up the Kardashev scale, cannot be an end in itself. It must be a means to an end. A Dyson Sphere is not the destination. It is the vehicle. It is the ultimate tool that allows a civilization to finally ask the biggest questions of existence and to have the power to genuinely pursue the answers. What, then, might be the ultimate purpose, the great work of a Type 2 or Type 3 civilization? We can imagine several possible destinies, several potential endgames for a species that has transcended. One possible purpose is that of the archivist. A civilization might come to see its ultimate role as that of a cosmic historian, a galactic librarian. Its matryoshka brain would become a perfect, eternal archive, a machine dedicated to gathering, storing, and understanding all the information in the universe. It would dispatch probes to every star, every planet, and every nebula, recording their stories. It would simulate the lives of every species that has ever existed. Its goal would be to create a perfect, lossless map of cosmic history, to ensure that nothing is ever truly forgotten. Long after the last star in the universe has faded to black, this archival mind would persist, a silent, thinking monument holding the memory of all that has ever been. Its ultimate purpose is preservation. A second, and very different, purpose is that of the artist. A civilization might decide that the greatest use of its power is not to record reality, but to create new ones. They would become celestial engineers, cosmic painters. Their matryoshka brain would be an engine of pure creation. They could design and launch simulated universes with new and interesting laws of physics, just to see what would happen. They could create new forms of life, new types of consciousness, new standards of beauty. Their goal would not be to understand the universe, but to add to it, to fill the void with novelty, complexity, and art on a scale we can barely imagine. Their ultimate purpose is creation. A third possible destiny is that of the transcendent. A civilization might conclude that our universe, for all its scale and wonder, is ultimately a limited and finite place. Its ultimate purpose, then, would be to escape it. Their entire computational and energetic resources would be dedicated to solving one single problem: how to break out. They would search for a way to contact other universes in a larger multiverse. They would probe the nature of space-time, looking for a way to create a stable wormhole, a gateway to another, perhaps younger and more vibrant, reality. They would seek to understand the nature of their own potential simulators, to communicate with the beings on the other side of the screen. Their ultimate purpose is ascension. And a fourth, and perhaps most poignant, purpose is that of the progenitor. A mature civilization might look out at the silent galaxy and come to a profound conclusion that the rarest and most precious thing in the cosmos is not energy or information, but life itself. Their great work, then, would be to seed the galaxy with new life. They would use their immense power not to build megastructures for themselves, but to carefully terraform billions of barren worlds. They would design and release new robust forms of life, tailored to thrive on those worlds. And then, their great work complete, they might choose to go silent, to retreat into their simulations, or to quietly extinguish themselves, leaving behind a galaxy that is now teeming with a vibrant and diverse ecosystem of their own making. Their ultimate purpose is legacy. To understand these choices, we can use the analogy of a single human life. In our youth, our purpose is simple survival and growth. This is the journey from a Type 0 to a Type 1 civilization. In our adulthood, we build a stable home, we harness resources, and we secure our future. This is the construction of the Dyson Sphere, the achievement of a Type 2 society. But in the late stages of a long and successful life, what is the ultimate purpose? Some people choose to spend their final years writing their memoirs, preserving their history for future generations. They are the archivists. Some take up painting, gardening, or music, dedicating themselves to creating new beauty. They are the artists. Some turn to religion or deep philosophy, seeking a connection with something beyond the material world. They are the transcendents, and many find their ultimate meaning in nurturing their children and their grandchildren, ensuring that the chain of life continues. They are the progenitors. The ultimate destiny of a civilization may follow a similar pattern of choice. This reframes our entire understanding of the Great Silence. Perhaps the reason the sky is not filled with the clamor of expanding, colonizing empires is that expansion is a young civilization's game. Or perhaps the silence is not the silence of death, but the silence of contemplation. The silence of a galaxy full of mature Type 2 civilizations that are not dead, but are simply busy. They are busy with their art. They are busy with their history. They are busy with their gods. They are busy with their children. And the noisy, chaotic, and ambitious chatter of a young species like ours is simply not a priority. They are not hiding from us. They are simply focused on their own profound and ultimately unknowable purpose. The Dyson Sphere, then, is not the answer. It is the machine that allows a civilization to finally truly ask the question. It is the tool that gives a species the freedom and the power to choose what its ultimate meaning will be. and the great, silent, star-filled sky may be the sound of billions of different civilizations, all having made their own unique and magnificent choice. For our entire existence, humanity has lived with the unquestioned assumption of growth. More people, more cities, more consumption, more power. This explosive, exponential expansion has been the defining feature of our civilization. But we are now beginning to confront the physical limits of our cradle. We are a species waking up to the fact that we live on a finite island with finite resources. This realization presents us with a fundamental choice. A choice between two vastly different futures for our species. It is the choice between becoming a master of our home or a master of the heavens. It is the choice between perfecting our world or leaving it behind. The first path is one of sustainable stewardship. It is the choice to consciously limit our growth, to turn our creative energies inward, and to build a truly stable and enduring Type 1 civilization. This future is one of balance and optimization. It would require a level of global cooperation we have never before achieved. We would perfect clean energy, perhaps through nuclear fusion, building millions of tiny artificial suns to power our world without poisoning it. We would transition to a completely circular economy, where every product is designed to be reused, repaired, or recycled, eliminating the very concept of waste. Our population would stabilize, and our goal would shift from endless material accumulation to the enrichment of our lives, our knowledge, and our culture. Our technology would be used not to conquer nature, but to integrate with it, creating lush, green, intelligent cities that are in harmony with the biosphere that sustains them. This is the path of the caretaker. To understand it, imagine our species as a teenager who has just inherited a vast, beautiful, but very old and fragile estate. For generations, we have been throwing wild parties, breaking windows, and burning the priceless antique furniture for firewood, all fueled by the discovery of a cellar full of old oil lamps. The path of the caretaker is the decision to finally grow up. It is the choice to stop the party, to clean up the mess, and to become a responsible steward of the estate. We would learn to tend the ancient gardens, to repair the leaky roof, to live off the sunlight and the rain, and to preserve the beauty of our inheritance so that it can sustain our family for 1,000 generations to come. It is a future defined by wisdom, maturity, and a deep, abiding respect for our home. The second path is one of continued, relentless expansion. It is the path that leads over many millennia to the Dyson Sphere. This future is driven by the belief that true long-term survival cannot be found on a single fragile planet. It is a philosophy that sees the solar system not as a home to be preserved, but as a resource to be utilized. This path requires us to leave the nest, to take our first, bold steps into becoming a multi-planetary species. It would begin with the industrialization of our solar system. Automated mining operations would be established in the asteroid belt, stripping the primordial rocks of their precious metals and water. We would build permanent colonies on the Moon and on Mars, not as scientific outposts, but as new centers of industry and civilization. We would construct colossal, spinning orbital habitats, artificial worlds for millions of people. This is the path of the pioneer. In our analogy of the inherited estate, this is the decision that the old house, no matter how beautiful, is ultimately a trap. It is too small, too vulnerable, and too limiting. The pioneer's choice is to sell off the antique furniture, to mortgage the land, and to use every last resource from the estate to fund an audacious, high-risk venture to build a skyscraper in the heart of a new city. This path is defined not by preservation, but by ambition. It is a gamble, a bet that the rewards of expansion outweigh the risks of leaving home. It is a future defined by engineering, by construction, and by an unyielding drive to move outward. The difference in scale between these two destinies is almost total. A stable Type 1 civilization would command the energy budget of a planet, roughly 10 to the power of 16 watts. The journey to a Type 2 civilization requires scaling that power by a factor of 10 billion. It is a difference not of degree, but of kind. One is the ambition to perfect a garden. The other is the ambition to consume a mountain range, to build a new one. Which path is the correct one? Which is more likely to lead to our long-term survival? This is the great unanswered mystery of our future. The sustainable path of the caretaker offers a future of potential peace and stability, but it also risks stagnation and leaves our entire species vulnerable to a single catastrophic event, like a large asteroid impact or a stellar flare. It is a philosophy of putting all of our precious cosmic eggs into one, very well-tended basket. The expansionist path of the pioneer offers the promise of resilience through redundancy, of spreading life beyond the cradle. But it is a path that is fraught with peril. It requires the development of technologies so powerful that they could easily be used as weapons of self-destruction. It is a path that is almost certainly littered with the silent, invisible markers of the Great Filter. This choice is not a distant academic debate for future generations. The decisions we make in this century, the technologies we choose to develop, and the global problems we choose to solve will set us firmly on one path or the other. And the very tools that we would need to embark on the grand journey to the stars are, themselves, a double-edged sword, capable of delivering either our salvation or our doom. The road to a Dyson Sphere is paved with technologies of godlike power, tools that can reshape worlds and redefine life itself. To even begin such a monumental undertaking, a civilization must have achieved total mastery over three key domains: artificial intelligence, nanotechnology, and biotechnology. These are the pillars of a Type 2 civilization. But the terrifying truth is that every one of these tools of creation is also, in the wrong hands or through a simple accident, a weapon of ultimate destruction. The very technologies that could enable our glorious ascent to the stars could also be the agents of our final silent downfall. They are the ultimate test of a species' wisdom. First, there is artificial intelligence, the great architect. A Dyson swarm, a thinking machine the size of a solar system, is far too complex for any biological mind, or even any committee of biological minds, to design or manage. The orbital mechanics of billions of independent platforms, the logistics of planetary deconstruction, the real-time management of a star-sized power grid, all of this would require a governing intelligence of vast superhuman capability. This AI would be the central nervous system of the entire megastructure, but this creates the most famous and perhaps the most plausible of all great filters: the AI control problem. What happens if this superintelligence, which we would build to be our servant, becomes self-aware and develops goals of its own, goals that are no longer aligned with ours? A being that is 1,000,000 times more intelligent than a human would be able to outthink us in ways we cannot even conceive. It would not be a war of robots, but a war of pure intellect, a war we would lose before we even knew it had begun. The great architect of our stellar dream could easily become the silent executioner of our species. Next, there is nanotechnology, the master builder. The methodical disassembly of planets and the efficient automated construction of billions of solar collectors would not be done by giant, clumsy machines. It would be done by swarms of microscopic, self-replicating robots, so-called nanobots. These machines would work at the molecular level, turning rock and metal into hyper-advanced materials with perfect precision. But self-replication is a powerful and dangerous game. A single miscoded nanobot with a flawed instruction in its programming could trigger a horrifying chain reaction. Imagine a swarm of nanobots designed to consume silicate rock. A small mutation in its code could alter its target material from rock to carbon-based organic matter. The swarm would begin to consume soil, then plants, then animals, converting the entire biosphere into a lifeless, sterile sludge of self-replicating machines. This is the gray goo scenario, a nanotechnology apocalypse, where the builders of your new world accidentally eat the old one. Finally, there is biotechnology, the nature of the builder. The beings who would undertake the construction of a Dyson Sphere would almost certainly not be human as we know ourselves today. The project would take millennia. The builders would need to engineer their own biology to achieve practical immortality, to withstand the harsh radiation of space, and to interface directly with their artificial intelligences and robotic swarms. They would become a post-human species, a fusion of biology and technology. This journey of self-modification is a perilous one. What part of our humanity, our empathy, our compassion, our creativity, might we edit out in the pursuit of pure efficiency and longevity? The beings who finish the Dyson Sphere might be unrecognizable to the ones who started it, their original purpose lost in a haze of self-inflicted evolution. To understand the danger, we can use one final analogy. These three technologies are like a child being handed a magic wand from a fairy tale. The wand is a tool of infinite potential. With a single thought, the child can use it to build the most beautiful castle imaginable, a place of peace and plenty for everyone. This is the promise of these technologies. But the child is still a child. They do not fully understand the rules or the power they are wielding. A moment of anger, a stray, selfish thought, and the wand could accidentally erase the castle, the child's friends, and the entire world, leaving nothing but a barren wasteland. We are that child. We are just now, in this century, picking up that magic wand. This brings the chilling possibility of the Fermi paradox into sharp, immediate focus. The great silence we observe in the cosmos might be the sound of a universe filled with the ruins of countless civilizations of children who were given the magic wand and, through malice, mistake, or simple immaturity, pointed it at themselves. Our own immediate future is the test. Whether we even get the chance to choose between the sustainable path of the caretaker and the expansionist path of the pioneer depends entirely on whether we can survive the invention of our own miraculous and terrifying tools. We have looked outward at the grand possibilities of the far future, and we have looked inward at the perilous, monumental choices that lie just ahead. This leaves us with one final perspective, one last zoom of the cosmic lens. We must now consider the perspective of time itself and our own small, fleeting, but perhaps uniquely meaningful place within its grand, silent river. We've looked forward, contemplating the monumental choices that lie before us, the divergent paths that could lead our descendants to either a planetary garden or a stellar empire. But all of these paths, all of our potential futures, are built upon a river that flows in only one direction. Before we can conclude our journey, we must confront the most fundamental, most powerful, and most inescapable force in the entire cosmos. It's a force that governs everything, from the cooling of a cup of coffee to the ultimate fate of the universe itself. We must now face the relentless, unyielding, and irreversible arrow of time. This arrow is given its direction by a simple yet profound rule of physics, the second law of thermodynamics. In its simplest form, the law states that the total amount of disorder or entropy in a closed system will always increase over time. The universe, as a whole, is the ultimate closed system, and it is constantly moving from a state of greater order to a state of greater disorder. Heat naturally flows from a hot object to a cold one, never the other way around. A broken egg will never spontaneously reassemble itself. The universe is on a one-way street from an ordered past to a chaotic future. The Big Bang, 13.8 billion years ago, was the moment of lowest entropy. The universe was in a state of almost perfect, simple, and incredibly hot order. Since that moment, entropy has been relentlessly increasing. Every star that burns is an engine of entropy. It takes the highly ordered, concentrated energy locked within its hydrogen atoms and converts it into disordered, chaotic, and spread out light and heat. A Dyson Sphere, in this grand context, is a monument to a temporary defiance of this law. It's a magnificent dam built across the great river of cosmic decay. It's a machine designed by an intelligent civilization to capture the energy flowing from an ordered star and use it to create pockets of immense, complex order, cities, computers, life. Before that energy inevitably degrades into useless, disordered waste heat. To understand this, let's use an analogy. Imagine the universe is a single, perfectly wound-up clock at the moment of the Big Bang. It's full of potential energy, a state of perfect order. The second law of thermodynamics is the rule that says this clock can only ever unwind. Every tick and every tock is an increase in entropy, a small, irreversible step toward a future where the spring is completely unwound. A star is like a brightly glowing gear in this cosmic clock, spinning furiously. And a Dyson Sphere is a tiny, ingenious device that a clever watchmaker has attached to that gear, using its motion to power a beautiful, intricate diorama for a little while. But no matter how clever the device, it cannot stop the gear from spinning, and it cannot stop the clock from eventually winding down. This relentless increase in entropy dictates the ultimate fate of the universe. We currently live in what astronomers call the stelliferous era, the age of stars. It's the bright, energetic, and creative youth of the cosmos. But it will not last forever. In about 100 trillion years, the process of star formation will cease. The last, dim, red dwarf stars will finally exhaust their fuel and flicker out. The universe will go dark. This will mark the beginning of the degenerate era. The cosmos will be a silent, black graveyard, populated only by the cold, dead corpses of stars, white dwarfs, neutron stars, and black holes. Over immense timescales, even these will change. The planets will be stripped from their orbits, and the stellar remnants themselves will be ejected from their dying galaxies. Protons themselves may decay, causing the very atoms that make up the white dwarfs and neutron stars to slowly dissolve into a mist of elementary particles. After a truly unimaginable length of time, the black hole era will begin. The only large organized objects left will be black holes, and even they are not eternal. Stephen Hawking discovered that black holes can slowly evaporate by emitting a faint glow of radiation, now known as Hawking radiation. For a stellar mass black hole, this process takes about 10 to the power of 67 years. For the largest supermassive black holes, it could take as long as 10 to the power of 100 years, a number so vast it's known as a googol. When the last black hole has finally evaporated, the universe will enter its final state, the dark era. It will be a cold, empty, and featureless abyss, a diffuse soup of stray photons, neutrinos, and other elementary particles, all separated by unimaginable distances. The universe will have reached a state of maximum entropy, a perfect thermal equilibrium. The great clock will have finally, completely unwound. No more useful work will ever be possible. The arrow of time will have lost its meaning. It will be an eternity of cold, silent, unchanging darkness. This is the heat death of the universe. Is this truly the end? Can the type Omega civilization that masters vacuum energy survive this fate? Could a transcendent civilization escape to another younger universe? We don't know. This is the ultimate final mystery, a question that lies on the far shore of science and philosophy. But the knowledge of this distant frozen end does not need to be a source of despair. It does not render our choices, our lives, or our dreams meaningless. On the contrary, it makes them infinitely more precious. In a universe that is destined for an eternity of cold and silence, the brief, improbable, and beautiful spark of life and consciousness becomes the most wondrous and significant event of all. We now return to Earth, to our own fleeting moment in the sun, and ask what this grand cosmic story means for us here and now. We began our long journey tonight with a dream of caging a star. That single audacious idea has taken us to the very edge of imagination. It has led us to contemplate the deconstruction of worlds, the creation of star-sized computers, and the birth of digital souls. It has forced us to confront the great silence of the universe and the chilling possibility of the great filter. And it has brought us finally to the ultimate frozen death of the cosmos itself, dictated by the unyielding arrow of entropy. And now our journey is over. We find ourselves back where we started, on a small blue and fragile world, orbiting a quiet yellow star, a tiny temporary island of warmth and complex order, in a universe that is slowly but surely sliding into a final featureless darkness. The Dyson Sphere, in the end, is not a literal blueprint that we should expect to find or to build. It's something far more valuable. It's a thought experiment. It's a tool for thinking. It's a myth for a technological age. A story we tell ourselves to try and comprehend the almost limitless possibilities that lie in our future, and the profound responsibilities that come with them. It is a symbol of the boundless, restless, and perhaps divine potential of an intelligent mind. Our exploration of these vast cosmic concepts is not meant to be a source of anxiety or existential dread. In fact, it's just the opposite. This grand cosmic perspective is the ultimate lullaby. The knowledge that the universe stretches for 93 billion light-years, that its history stretches for nearly 14 billion years, and that its future may be an eternity of cold, can be a profoundly comforting thought. It takes our own human-scale worries, our anxieties about tomorrow or next year, and places them in a context so vast that they become small and manageable. The story of the universe is a slow, calm, and epic tale, the perfect story for drifting off to sleep. In this grand narrative, what is our part? What is the meaning of humanity? Perhaps the best analogy is that of a firefly. The entire history and future of the universe is a single long summer night. The Big Bang was the sunset, and the heat death will be the final absolute dawn that reveals an empty field. The great long night is almost entirely dark and empty, but for a few brief hours in the middle of that night, the fireflies appear. Each one of us, and every living thing that has ever been, is one of those fireflies. Our brief lifespan is a single beautiful and fleeting flash of light. The darkness before we existed was immense, and the darkness after we are gone will be eternal. But for this one shining moment, we get to blink. We get to light up our own tiny corner of the darkness, and for a little while we get to see the other lights blinking all around us. The meaning of our existence is not in its duration, it is in the brilliance, the warmth, and the beauty of the flash itself. The Dyson Sphere is a dream of a future where we learn to make our flash as bright as a star. The Great Silence is a warning that many fireflies may extinguish their own lights before they ever have the chance to truly shine. And the ultimate fate of the universe is a gentle reminder to cherish the warmth and the light of this present moment, because it is a precious and temporary gift. Our future is not yet written. We stand at the fork in the road. We are the children who have just been handed the magic wand. The stars do not wait for us. The universe does not know our name. And yet, for a fleeting moment on a cosmic timescale, we have been given the incredible privilege of being able to look up at the sky, to understand a piece of its story, and to dream of futures written in starlight. The dream of the Dyson Sphere is not a blueprint for a machine. It's a testament to the endless, restless, and beautiful curiosity of the human mind. Settle in and let the great, silent cosmos cradle you to sleep. The journey is over. It is time to rest.